So the topic of today's video will be homogeneous linear differential equation with constant coefficients, right? And as we studied in our last video, that a difference equation is nothing but it is just a recurrence relation, or we call it difference equation when nth term is related to the previous term, right? So I will start with the general homogeneous linear difference equation with the constant coefficient, right? And that is of this form. An equation of the form y n plus k plus p1 and y n plus k minus 1 plus p2 y n plus k minus 2 plus p k y n equal to f n, and let me call it equation number A, right? And here the coefficients p1, p2 up to pk are constant because we are dealing with the difference equation with constant coefficients, right? And we have here this function fn, right? And since we are interested in finding the solution of a homogeneous difference equation, so I should set this fn equal to 0, right? If fn equal to 0, then this difference equation A is said to be homogeneous, right? And all of these, I will write it here, these pi, all of them, I will start from 1 up to k are constants, right? Okay, so we are interested in finding the solution of this difference equation, right? So I will take a smaller difference equation of order 2. You know that the order of a difference equation is just the difference of these numbers at n plus k minus n, so it is a difference equation of kth order, right? And if I consider a difference equation of order 2, that will be of the form y n plus 2, in place of k I will have 2, right? And here I will have p1 yn plus 1 and p2 yn equal to 0, right? We are considering the case when the right hand side is 0 for homogeneous difference equation. So we need the solution of this difference equation, right? And we claim that suppose yn equal to alpha to the power n be its solution, right? And why we considered this alpha to the power n is its solution? The first thing is that we know that a difference equation having right hand side equal to 0, obviously yn is equal to 0 is the solution of this equation. If you substitute yn equal to 0 here, this term will be 0, yn plus 1 will be 0, and yn plus 2 will be 0. So all of the three terms in the left hand side are 0, and 0 equal to 0 will be satisfied automatically. So 0 solution is the solution of this difference equation. The first thing is that this is very similar to the theory of differential equations. When the right hand side is 0, you say that the 0 solution is always a solution of a differential equation, and similar is the case with this one. But we are interested in finding a non-zero solution, right? In real life or in practical problems, we seek for non-zero solutions, and that's why I have taken this alpha to the power n. This is a kind of exponential function which is not equal to 0 until and unless you get alpha is equal to 0, right? So this is the solution, and this is a non-zero solution, right? Non-zero solution. And one more thing why I have taken particularly this, because I know that since if I operate yn plus 1, if I write yn plus 1, then it will become alpha to the power n plus 1, or you can write it as alpha times alpha to the power n, right? Or if you write yn plus 2, then you will be getting yn plus alpha n plus 2 equal to alpha square times alpha to the power n. So this is the reason why we have chosen this alpha to the power n, because I know that if I calculate yn plus 1, that will be constant times the original function. If I calculate yn plus 2, that will be again constant times that original function, and for all yn plus k values, that will be alpha to the power k into alpha to the power n. That's why we have chosen this function especially, right? As you choose that y equal to e to the power ax or e to the power mx in case of a differential equation, because you know that the derivative of an exponential function e to the power mx is just the constant multiple of e to the power mx, right? So the same reason can be used here, right? And I will put these values in this equation. Let me call it equation number 1. Substitute in equation number 1, that will produce alpha square, or alpha square will be, sorry, alpha to the power n will be taken common. If you plug these values here in this equation, is that here, then alpha to the power n can be taken common, right? And inside bracket you will have alpha square plus p1, yeah, and where is that, alpha plus p2 equal to 0, right? On plugging these values here in this equation, you will get this. And since these are two product terms and the product is equal to 0, so I will say that this is equal to 0 because I know that this is not equal to 0. Why this is not equal to 0? Because you know that this is a non-zero solution, so this has to be 0, right? So again, this is very important. Why we considered this yn equal to alpha to the power n as a solution? Because it is a non-zero solution, and that is also helping us at this point, right? You cannot write directly that this factor is equal to 0. You should verify that this term is a non-zero term, right? Okay, so that will give me alpha is square plus p1 alpha plus p2 equal to 0. As you already know that alpha to the power n is never equal to 0, right? Okay, so this is called auxiliary equation or characteristic equation, right? Auxiliary or characteristic equation, right? And you can see that this is a quadratic equation in alpha, and from the theory of quadratic equation, a quadratic equation may have distinct roots, real roots, equal and real roots, and complex roots. So there will be three cases after this. The first case one is case 1, if alpha 1 is not equal to alpha 2 are roots of this equation. Let me call this equation or roots of equation number 2, roots of second, right? Okay, and if these are the roots of this equation, then since you claim that, where is that, you claim that this is the solution, and if you got alpha 1, then alpha 1 to the power n be the first solution, and another value is alpha 2 to the power n be the another solution, right? Then alpha 1 to the power n and alpha 2 to the power n are its solutions, right? Okay, and since these are two solutions and both of them are independent solutions, why we are calling them independent? Or you should know, when we call two functions as independent functions, you just take their ratios. If their ratio is a non-constant term, then we say that the functions are independent. If you take the ratios of these two, and you will get I think alpha 1 by alpha 2 to the power n, so that is not a constant, so we can say that both of them are linearly independent, that is linearly independent solutions, right? So therefore the complete solution will be given by their linear combination yn equal to c1 alpha 1 to the power n plus c2 alpha 2 to the power n is complete solution, right? Where this c1 and c2 are arbitrary constants, right? So this will be the solution when we will have distinct roots, right? And what happens when we get equal roots? That is case number 2. Case 2, if alpha 1 equal to alpha 2, right, are real roots, and these are also real roots of equation 2, but they are equal, right? In that case, either you will write alpha 1 to the power n or you will write alpha 2 to the power n, but in that case they will be dependent, because alpha 1 equal to alpha 2, and when you will take their ratios, that will be equal to 1, right? So in that case, the two solutions, alpha 1 to the power n or alpha 2 to the power n, are linearly dependent, right? So I have to seek another solution, or second solution that should be independent with this one, right? Then alpha 1 to the power n is only solution. Just one solution will qualify. We will write the solution as a linear combination of two independent solutions, right? But here we are getting only one solution as independent. So we have to create another solution which should be linearly independent with this one, right? So there is a reasoning at this point. I will write that. Now n times alpha 1 to the power n will be the other Li solution, right? And the reason for this point, n times, why I multiplied with n, again the reason is same as we study in the theory of differential equation. When we have one solution y1 and the second solution can be obtained by just multiplying it with x, because you know that the ratio of two independent solutions should be non-constant, right? And the best choice for that ratio to be x, right? And why it is x? Because x is non-constant, right? And the reason is similar to that, the theory of differential equations, right? That's why I have written n, because in place of x we have n, right? So this will be the another linearly independent solution, and therefore the full solution will be given by C1 multiplied by first solution, that is alpha 1 to the power n, and C2 multiplied by with the second solution, and that is n times alpha 1 to the power n. And ultimately you can take alpha 1 to the power n common, C1 plus C2 n multiplied by alpha 1 to the power, and this will be the solution, right? Where C1 and C2 are again arbitrary constants, right? And the number of arbitrary constants that are involved in a solution of a difference equation is just equal to the order of the difference equation. You can see the order of this differential equation is equal to 2, right? So that's why in all cases I will be getting two arbitrary constants, right? Okay, and if we have three roots, alpha 1 equal to alpha 2 equal to alpha 3, and for that obviously my this auxiliary equation should be cubic in nature, and in that case the solution should be written as C1 plus C2n plus C3n square, and then multiplied by alpha 1 to the power n, right? And case number 3, if alpha 1 equal to a plus iota b and alpha 2 equal to a minus iota b, right? It means that the roots are complex, are roots of equation number 2, right? And since the roots are complex, but you can see that the roots are distinct, right? Because this is not equal to alpha 1 is not equal to alpha 2, so it is very similar to case number 1, right? Since alpha 1 is not equal to alpha 2, so I will use this result, right? Therefore yn equal to C1 times alpha 1 to the power n plus C2 times alpha 2 to the power n is solution, right? Since we know that the roots are not equal this time, so it will be same as case number 1, right? But on putting the values of alphas here, I will get C1 times a plus iota b and C2 times a minus iota b to the power n, right? And it can be simplified to a more closed form if you put a equal to r cos theta and b equal to r sin theta in order to get the solution in terms of theta, right? Or and r also. To simplify it, so, however, this is also correct, right? To simplify it, you just put a equal to r cos theta and b equal to r sin theta, such that if you square and add these two, you will get r is equal to a square plus b square whole to the power half, right? And if you divide these two, you will get theta equal to tan inverse b by a, right? Okay, and putting these values here in my solution, this will give you yn equal to, see here, C1 times a plus iota b. The value of a is this one and b is this, so r will be taken common like this, and here we have cos theta plus iota sin theta whole to the power n, and similarly C2 r to the power n cos theta minus iota sine theta whole to the power n, right? Okay, and after that I think r to the power n should be taken common. R to the power n should be taken common in C1, and here you can use that De Moivre's rule. This n goes inside the angle, you know that, right? So it will become cos n theta and plus eta sine theta. Okay, and from here I will get C2 C1 plus C2 cos n theta. Okay, C1 plus C2 cos n theta, and from here the second term will be, I think, eta C1 plus eta C2 sine n theta, right? On simplifying it, you can see that that will produce cos n theta plus eta sine n theta, and cos n theta minus eta sine n theta, and then taking common cos n theta and sine theta, you will get this, right? So C1 plus C2 is sum of two constant. I should replace that by a new constant and let the constant be capital A, right? The C1 plus C2 is written as capital A cos n theta, and this eta C1 plus eta C2 is written as capital B sine n theta. So this is your solution, right, in terms of r and theta. Here you should remember the value of r, or you should just plug the value of r here, right, where r equal to square root of a square plus b square, and theta is equal to tan inverse b over a, right? So there is a theory of solution of homogeneous linear difference equation. So the idea is to convert the given difference equation into an algebraic equation like this one. You can see that is an algebraic equation, quadratic, it may be cubic, that will depend on the order of this difference equation, and then you can use that same theory as you used in theory of differential equation, right? So I will take examples of this thing. Example number 1, solve, and the difference equation is y n plus 2, let me write 2 here, minus 5 times yn plus 1 plus 2 times yn equal to 0, right? You can see that this difference equation is of order 2 because the difference of these suffixes, this is n plus 2 minus n is equal to 2, right? And that's why the order is 2, right? And all of the coefficients are constant, that's why we can use the theory, and the right hand side is 0, right? And I will add two conditions also. So you are given that y0 equal to 0 and y1 equal to 1, right, in order to find those arbitrary constants, because there is a second order difference equation, so you will be having two arbitrary constants in your answer. In order to find those constants, you should use these conditions, right? So solution will be given by let me start with that alpha to the power n, right? Let yn equal to alpha to the power n be its solution, and you know that alpha to the power n is not equal to 0, right? So if you plug these values, I mean yn equal to this much, and yn plus 1 will be equal to alpha to the power n plus 1, yn plus 2 will be equal to alpha to the power n plus 2, and plugging here, this gives you alpha to the power n will be taken common, and from here you will get 2 alpha square minus 5 alpha plus 2 equal to 0, right? And at this point you know that this function cannot be 0 from here, so this will be equal to 0, right? Implies that 2 alpha square minus 5 alpha plus 2 equal to 0, and that is called your auxiliary equation, or you may write it directly also, right? And on factorization it will give you 2 alpha square minus this is equal to 5, so 4 alpha minus, okay, equal to 0, and that will produce, I think, 2 alpha will be taken common, and alpha minus 2 and 2 alpha minus 1. These are the factors of this equation, and alpha equal to 1 by 2 and another will be 2, right? So you got two distinct roots, and if we get distinct roots, then we should use that formula obtained in case number A, right? Therefore the solution will be of the form yn equal to c1 times the alpha 1 to the power n plus c2 times alpha 2 to the power n is the solution, and it's the general solution. It is containing c1 and c2. We call it general solution. C1 and C2 are present here. A general solution. We have C1 and C2 are arbitrary constants, right? And I will find these arbitrary constants with the help of these two conditions. Since y0 equal to 0, that will give me, put y, see the suffix here, we have n equal to 0. So I will put n equal to 0 in this equation, and at this y0 will be replaced by 0. So I will get 0 equal to, because y0 is equal to 0, and c1 into half to the power 0, that will become c1, and that will become c2, right? So this is the first equation, or this will give you c1 equal to minus c2. And similarly, the next condition, y1 equal to 1, this time you will put n equal to 1. See the suffix of this y, put n equal to 1 in this equation, you will get y1, and y1 should be equal to 1 equal to c1 into half, okay, and twice of c2 if I'm not wrong. And I will use this, c1 is equal to minus of c2, so that will produce 1 equal to minus c2 by 2 plus 2 c2, right? So that will ultimately produce 3 c2 by 3 by 2, yeah, 3 by 2 or 2 by 3. So c2 will be equal to 2 by 3, and since c2 is equal to 2 by 3, so therefore c1 will be equal to minus 2 by 3, and I will put these values here in my solution, right? Therefore yn equal to minus 2 by 3, 1 by 2 to the power n, and plus 2 by 3, 2 to the power n is solution, right? The solution satisfying this particular condition, right? So taking another example, this time I have used the difference equation where I got two distinct roots, but this time I will use the equation where I will get repeated roots. In order to use that case number 2, example number 2, if I take the equation, solve alpha n plus 2, sorry, not alpha, yn plus 2 minus 4 yn plus 1 plus 4 yn equal to 0, right? Okay, and generally we have a condition on n is greater than or equal to 0, right? So generally it is written, and for this it should be, yeah, n is greater than or equal to 0, right? You know that this n is a non-negative integer, it will 0, 1, 2, 3 and so on, right? Solution. Its auxiliary equation will be, I will write that equation directly, right? Auxiliary equation will be alpha square minus 4 alpha plus 4 equal to 0, right? I have skipped these steps, right? Okay, so that will produce alpha minus 2 whole square equal to 0, or alpha equal to 2, 2, right? So these are the repeated roots, and when we get repeated roots, the solution is of this form, c1 plus c2n multiplied by that root to the power n is solution, is general solution, right? So this is a solution. Taking another example, example number 3, and solve. If I take y n plus 4 minus 4 times yn plus 3 plus 6 times yn plus 2 minus 4 times yn plus 1 plus yn equal to 0, right? And again n is greater than or equal to 0, right? Solution. Again starting with the same thing, let yn equal to alpha to the power n be the solution, where alpha to the power n is not equal to 0, and then plugging that alpha to the power n here, and knowing the fact that this alpha to the power n is not equal to 0, I will get an auxiliary equation, like auxiliary equation alpha to the power 4 minus 4 alpha cube plus 6 alpha square minus 4 alpha plus 1 equal to 0, right? So you have got a biquadratic equation, an equation of degree 4, right? So you have to factorize it. First thing is that, and yeah, there are 2 or 3 methods in order to solve this. First thing is that if you are able to identify this formula is of actually alpha minus 1 whole to the power 4. Yeah, alpha minus 1 whole to the power 4. But if you are not able to identify this formula, then what you should do, you should apply that rational root test. And what is that test? You focus on this constant term, this is 1. So the possible roots are 1 or minus 1. Either 1 will be its root or minus 1 will be its root. So this is a kind of hidden trial method, right? But calculated hidden trial. Calculated in that sense, you just guess a number which divides this number, right? This number is 1. So obviously the possible roots are plus 1 or minus 1. 2, 3, 4, 5, 6, they cannot be the roots of this equation. So don't waste your time. Okay. So I will start with plus 1. So if I put plus 1 here, I will get 1 minus 4 plus 6 minus 4 plus 1. Yeah, I think 1 minus 4 plus 6, something is missing. 1 minus 4, 4 cube, 1 minus 4, 6. Yeah, okay, 0. Putting alpha equal to 1, I am getting 0, right? So clearly, alpha equal to 1 satisfy this equation, right? And if I write clearly, then it means something, that alpha equal to 1, why only alpha equal to 1, why I have only tested alpha equal to 1, why not alpha equal to 2, right? So you should remember that rational root test and satisfy this equation. So we can say that alpha minus 1 is its factor, right? One of the factors is alpha minus 1, and find the other factors. Either you divide this polynomial by alpha minus 1, but that will be a long process, because when you divide this polynomial by alpha minus 1, you will get a cubic polynomial, and then again to factorize a cubic polynomial, that is not an easy task. Again you have to use that hidden trial method, right? So another point is that if I know that alpha equal to 1 is the root of this equation, should I check with alpha equal to minus 1? Yes, if I put alpha equal to minus 1, this term is positive, this term positive, 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 positive. So that cannot give you 0, right? So it is clear that alpha equal to minus 1 is not the root of this equation. Only alpha equal to 1 is the root. Okay, so this is the one root. Now the another possibility is that is it possible that alpha equal to 1 is a double or triple root of this equation? This is also possible. So to see that possibility, what we do, we just differentiate this polynomial in our mind, and we will just plug that alpha equal to 1 in that derivative. If that becomes 0, it means that alpha equal to 1 is a double root, right? And again we find its triple derivative, third derivative and fourth derivative, and we just go on plugging this alpha equal to 1 in those derivatives. If we get 0, 0, 0 every time, it means that alpha equal to 1 is a 0 of order, that much order, which is the first non-vanishing derivative. It's the same as we use the theory of finding the zeros, order of zeros and poles in complex analysis, right? Okay, so alpha equal to satisfies this equation, right? That is correct. Okay, now I should call this polynomial as f alpha, right? Let f alpha, I am calling it f alpha, or should I write it h alpha? Okay, h alpha. Alpha to the power 4 minus 4 alpha cube plus 6 alpha square minus 4 alpha plus 1, right? And I calculate f h dash alpha derivative, that will be 4 alpha cube minus 12 alpha square plus 12 alpha minus 4. Now I will calculate h double dash alpha, that is 12 alpha square minus 24 alpha plus 12, then h triple dash alpha, that will be 24 alpha minus 24, and finally h fourth derivative of alpha, that will be 24, right? So calculating its derivatives, obviously up to fourth, because this is a polynomial of degree 4, and putting 1 everywhere, right? And you can see that if you put 1 here, you are getting 0. It's already tested. And if you put 1 its derivative, then you will again get 0. You can see that, right? This is equal to 0. And similarly, if you put 1 in its second derivative, again you are getting 0. And here also up to third derivative you are getting 0. But its fourth derivative at 1 is not equal to 0. So what does this information convey? It conveys that alpha equal to 1 is a 0 of this polynomial of order 4, right? So I will write that. Therefore, alpha equal to 1 is a 0 of this h H alpha of order 4. Why order 4? Because the first non-vanishing derivative was of fourth order, right? If you have studied that complex analysis a bit, then you will understand, right? Order 4, okay. Therefore, alpha equal to 1, 1, 1, 1 or its root. So you have only one root, 1, 1, 1, 1, right? So I will write its solution. Yn equal to C1 plus C2n C3n square C4 n to the power 4, right? And n cube, sorry, 1 to the power n, right? And 1 to the power n is again 1, you know that. So ultimately it will become C1 plus C2n C3 n square C4 n cube is general solution, right? Okay. So I will take my last example when we'll get complex roots, right? Example number 4, solve yn plus 2 plus yn equal to 0 and n is greater than equal to 0, right? So in order to solve this, we'll start with that. Let yn equal to alpha to the power n be its solution, and alpha to the power n is not equal to 0 because you are searching for the non-zero solution. And when you plug this here, you will get this gives alpha to the power n will be taken common, alpha square plus 1 equal to 0, right? And you know that this is not equal to 0, so this factor has to be 0. It implies that alpha square plus 1 equal to 0. This is called the auxiliary equation or characteristic equation. And when you solve this, you will get alpha equal to plus minus I, right? So this time we have got complex roots and both of them are distinct. So I will either use that formula directly, if you remember that formula. I will use that formula directly, right? Therefore, solution is yn. I think outside I had r to the power n, if I remember that correctly, r to the power n, and inside I had a cos n theta plus b sin n theta, right? And what is that r? Yeah, r was where r equal to square root of a square plus b square, and I should write it as 0 plus minus 1 iota, right? So that my a will be equal to 0 and b will be equal to 1. So a square plus b square, and that will be equal to 1, right? And theta was equal to tan inverse b upon a. What is b? B is 1 and a is 0. So tan inverse infinity, that will give me pi by 2, right? So I'll plug these values r and theta here in my solution, right? Therefore, yn equal to r is 1, so 1 to the power n will be 1, that is fine, and a cos n pi by 2 plus b sin n pi by 2, right, is general solution where capital A and capital B are arbitrary constants, right? So this is what the solution of a homogeneous linear difference equation with constant coefficient appears as. And we have only 3 cases: the real and distinct roots, right, where the solution is written in this form. Where is that? Distinct roots, yeah. And then repeated roots, the solution is written in this way, and then complex roots, right? So this is it for this video. In the next video we will be considering the non-homogeneous linear difference equation where the right hand side is non-zero, right? That will be the part of our next video. For this video, thanks.